Hello and welcome to your Equilibrium podcast. We're going to go over what equilibrium is. We're also going to talk about how to write an equilibrium expression and then how to interpret your k-value for an equilibrium expression. So up until this point, we've thought of reactions as being something where your reactants are going to interact with each other to form a product. And we think about this reaction as happening to completion. So all the reactants are going to react until you form as much product as you can form, and that's the end of it. Sometimes, however, you have reactants that can react to form products, and then those products react with each other to do the reverse reaction and reform reactants. So this is when we start to talk about reversible reactions and equilibrium. So equilibrium occurs when the rate of the forward reaction, so your reactants reacting together to form products, and the rate of the reverse reaction, the products reacting to reform the reactants, are equal to each other. So as you're making products, you're also reforming your reactants, and this is where it gets a little bit trippy. So we could write this a reversible reaction both ways. We could say that hydrogen gas and iodine gas can form this product. Well, we know that this product also will break down into hydrogen gas and iodine gas. So not only are we using these two reactants to form products, but the product can also break down through the reverse reaction and reform the reactants. So instead of having to write two separate equations, we can use a double-headed arrow instead. So Word lets me use this arrow, which isn't as pretty as the one I'd like to show you. To say that a reaction is reversible, you're going to draw double-headed arrows like this, where you have a half arrow going in one direction and a half arrow going in the other. So we are no longer using a single-headed arrow, which assumes that your reaction is going to completion. But now, okay, when we talk about equilibrium, the rate of the forward reaction to form the products is equal to the rate of the reverse reaction to reform the reactants. All right, so let's look at a visual of what's going on. Here in number one, we are seeing A is represented by these blue spheres, and B is represented by the red spheres. So over the course of time, the difference between 1 and 2 is that A is being slowly converted to B. So slowly we see this A being converted to B over a period of time. Typically when we think about reactions, we would stop as soon as all of A is converted to B. But since this is an equilibrium and it's a reversible reaction, we know that B can be reconverted back into A. So over time, as we notice in image 3, we are increasing the amount of B. Well, now that we have a higher number of that, you're going to see a shift, and you're going to see some of those B molecules being converted back into, this one specifically, is getting converted back into A again. So A is being converted to B, your product. B, the product, is being converted back into A over time. They're at equilibrium when the rate of A being converted to B and B being converted back to A is the same or equal. All right, so when we think about an equilibrium expression, I want you to think about the fact that the net concentrations of your reactants and your products are not going to change at equilibrium. But we can use your concentration of your reactants and your products to define an expression which we call the equilibrium constant, which is represented by this letter, that letter K. In our class, we use KEQ. You may just see that written as K, but that is your equilibrium constant. So this is going to give us a characteristic value for reactant at a given temperature. For this class, we're not going to change the temperature. We're not going to mess around with that. We're just going to assume everything is happening at the same temperature, so we don't have to add in that variable as well. We're also not looking at the number of moles in a given quantity, but because we're talking about concentration, we're actually looking at the number of moles per liter. Okay, when you see brackets on here, that's representing concentration. And because it's moles per liter, we're actually talking about molarity. Molarity is shown with a capital M, and molarity is moles per liter of something. That's how we define concentration. So Let's start by using a very generic equation where your lowercase letters here are representing coefficients. And I wish C looked a little different. And your uppercase letters are representing reactants on this side and products on this side. So in order to write our equilibrium expression, as you can see at the top, your products, the concentration of your products are going to go on top, and the concentration of your reactants are going to go on the bottom. We're going to multiply all the reactants together and all the products together, and we're going to raise them to the power of the coefficient. So this is again why it's really important that you're able to balance an equation properly, or you're going to get numbers that don't quite work. So to write our equilibrium expression, we put in brackets our substance, the concentration of our substance. So this is product C and product D, and we are raising that to the power of our coefficients. Oops, there's our coefficient. Okay, and then we're going to do products over reactants. So as you can see on the bottom, I have the concentration of this reactant raised to the power of the coefficient. This is your general equation. This is a little bit easier again in practice, as everything is. So let's take a look at a sample equation. We're going to use the same reaction that we had on the previous slide, where hydrogen gas and iodine gas are reacting to form a single product. It's a reversible reaction. So we're told in this problem that the concentration of H2 is 0.25 molar. That's always how we define concentration, as molarity. I2 is 0.25 and HI is 0.5 molar. So to set this equation up, I'm going to start by writing kind of a generic equilibrium expression. So I know that I'm going to put my products on the top, and I'm going to have the concentration of HI, and it's going to be raised to the power of the coefficient. Okay, on the bottom, I'm going to put my reactants. So I'm going to have the concentration of H2 raised to the coefficient. There is no number in front, so I can assume that it's raised to the first power. I don't actually have to write this, but it might be helpful in the beginning just to ensure that you've looked to write the one to kind of remind yourself, yes, I've looked at that and I've acknowledged that there isn't a number to put up there. I'm going to multiply the concentration of H2 by my other reactant, I2, and again, there's no number in front, so I'm going to raise that to the first power. So now we have kind of our skeletal equation, and what we're going to do next is we are going to fill in the concentrations that we were given in this problem. So on top, the concentration of HI that I was told is 0.50. And I'm going to not include my units in this. When you have a K value, it's not going to include units because the units will really vary depending on what reactants and products you have, and because it's a constant, we don't report it in terms of units. So one time you get to leave units off. So I'm going to raise that to the second power. And now I'm going to fill in the concentrations of H2 as told in my problem, which is 0.25, and it's raised to the first power, so I'm going to go ahead and leave that off now, times the concentration of I2, which is also 0.25. So now it's just a matter of plugging these numbers into my calculator. So 0.5 squared divided by 0.25 times 0.25. Just roughly, this is going to give me 0.25 on the top and 0.0625 out of my calculator on the bottom. I'm going to divide the top by bottom, and my K value is equal to 4.0. I am reporting to 2 sig figs because each of my concentrations are 2 sig figs. So now that we learned how to write an equilibrium expression and find an equilibrium constant, we can talk about what does a K value actually tell us. So if your K value is incredibly small, and we're talking smaller than 0.01, it tells us that the reactants are favored, or the equilibrium lies to the left side, the reactant side of the reaction. So essentially at equilibrium, when your forward reaction and your reverse reaction rates are equal to each other, it's telling you that the concentration of the reactants is greater than the concentration of the products. All right, so if your K value is larger than 1, and I don't mean just like it happens to be 2, but I mean it's larger than 100, it's a really big number, then your products are favored, or the product side or the right side of the equation is favored. What this essentially means is that the concentration of your products now is greater than the concentration of the reactants at equilibrium when the forward reaction rate is equal to the reverse reactions rate. All right, so if your K value is about 1, and I'm using that number very loosely because I really mean about 0.01 to about 100, both your reactants and products are present in about equal amounts. So we can use this to kind of figure out if this reaction were to happen and it goes to equilibrium, am I going to have more reactants, more products, or am I going to have equal concentrations of both? So one thing to keep in mind when we are doing our equilibrium expressions is that your solid and liquid states are not going to be included in your expression or your calculations. Only gases are going to be used in the expression as well as the calculation. And the reason for this is because your concentrations of solids and liquids are going to stay pretty constant, and they're going to stay the same at equilibrium. And the only change that we're going to see is in gases.